Hello and welcome. My name is Lars Roveda and I'm currently a postdoc at EPFL. I will present recent work with Jana, Fritz, Christoph and Robert, and this is about block-structured integer and linear programming. In our setting, we are given n polytopes q1 to qn, and let us assume for simplicity that they are all in dimension t. We are interested in optimizing over each of these polytopes simultaneously, but they are not quite independent. There are a few linear equations that link together these polytopes. More formally, we define a polytope P, which is the Cartesian product of these n polytopes, but there are also R many linear equations, and we think of R as being very, very small. These linear equations are given by matrices A1 to AN and the right-hand side B. So we require that sum of AI xi is equal to B. One natural question that arises is, suppose that you can optimize efficiently over each of these QIs. Well, can you also optimize efficiently over this block-structured polytope? The second question is kind of similar. Suppose you have algorithms that optimize efficiently over only the integer solutions of each QI. Well, can you also find efficiently the optimal integer solution of P? And this gets hopeless very easily because you may run into problems like knapsack. So to avoid that, we require that all the entries of A1 to AN are small. In this paper, we present algorithms for both cases, and we show that under reasonable assumptions, you can answer both questions with yes. And that the overhead of these additional few rows is rather small. One notable example of this kind of setting is the n-fold integer programming problem. And in this problem, each of the QIs are defined by a linear program in standard form, but this linear program itself has only very few rows. So here we use a matrix BI, and each of the QIs is defined by a linear system, BI xi equals B, and BI has only very few rows. You can, of course, also write this as a single constraint matrix, and then the blocks A1 to AN appear on a horizontal line, and the matrices B1 to Bn are aligned on a diagonal. And this problem has been studied very often in recent literature, and the typical parameters that are required to be small are the entries of A and AI and BI, as well as the number of rows of the matrices AI and the number of rows of the matrices BI. I want to mention that the setting that I introduced initially is somewhat more general. Especially the BIs don't have to have very few rows. You can, for example, have some recursive block structure where the BIs themselves are again, block structured integer programs. This problem has mostly been studied in respect to the integer programming variant. Let me quickly compare how our techniques relate to the previously used techniques. So previously, the typical approach was to first prove strong proximity between LP solution and integer programming solution. That means we prove that given some LP solution, there's also an integer solution where you don't have to change the variables very much. Here, the typical proximity is that this distance is in the order of nt times the function in the parameters. And there are also examples that show that the naive LP is not independent of n. Then you solve the LP variant with some linear programming algorithm, for example, the ellipsoid method. And then you devise a certain iterative augmenting framework which slowly converges to the optimal solution. This framework usually requires some linear number of repetitions until you arrive at the optimal solution, and it is also not independent of the encoding size of the integers in the problem. So as I said, only the entries of the matrices are required to be small, not the coefficients of the optimization directions or the right-hand side. And here we are not strongly polynomial. This requires some dependency on the size of the encoding. So typically, the best known algorithm, it produces an optimal solution in almost linear time and the number of variables, some dependency on the encoding size of the largest entries, and some function in the parameters, plus, of course, the time that you require to solve the LP variant. I want to mention that there is indeed a strongly polynomial algorithm, but in order to avoid the dependency on the encoding size, it requires a much larger dependence on the number of variables. Our methods are quite in contrast to these, because what we do is we introduce a new, stronger LP relaxation. And for this relaxation, we can actually show that the proximity depends only on the parameters and not on the number of variables. We also give a sophisticated algorithm that solves the LP case in a much faster time than like a black box LP algorithm. And now, given this LP solution, we are able to find the optimal integer solution in time roughly linear in number of variables times the parameters. We are able to avoid the dependency on the encoding size, maintaining the near linear dependency on the number of variables, and we do not have any overhead because of solving the LP, because this is already integrated in a sophisticated algorithm. One other advantage of our techniques is that they are highly parallelizable. Our algorithm can also be run in parallel, and this is in contrast to the previous works where, because of the iterative augmentation, you need at least a linear number of sequential operations. I'll quickly sketch how the dynamic program looks like and why it is so helpful to have that the proximity depends only on the parameters and not on the number of variables. So take a look at one of the QIs, and we want to produce some solution that is inside this QI. And of course, this solution will produce some right-hand side on the linking constraints on the R many equations that link all these polytopes together. Now, this right-hand side that one of these polytopes produces, we can guess it within some very small number of candidates, because we know that it must be similar to the right-hand side that the LP solution produces. So the number of these candidates is only a function in the parameters to the power of R. We can essentially guess this. And for each of the guesses, we solve the problem for each of the QIs. Then in a binary tree, we just combine iteratively the partial solutions. So we take of two polytopes each solution that each of them produced, and we combine them pairwise. And that way we get solutions for various right-hand sides of the combination of the two polytopes, and of each we store the best of them. And this way we trickle down until we have solutions for the complete problem. This gives us in the end a running time that is some function in the parameters to the power of R times the total sum required to optimize over each of the QIs. Well, if you had a proximity that depends also on the number of variables, then with this approach you would get some uh, running time of the form n to the power of R or similar, and that we want to avoid here. Next, we will talk about the stronger relaxation. But first, how would the naive approach look like? So our integer program, it has some R many linear constraints. And in addition, we want that each xi is in qi and also integer. So for natural LP relaxation, you could just omit the integer constraint all in all. And there are some good news, because suppose you have some vertex solution for this LP, then you know that almost all of the parts xi must also be vertex solutions to the polytopes qi, because if you had more than R many partial solutions xi, then which are not vertices, then it means that there is some line where you can move a little bit the solution and remain feasible. Now, if you have more than R of these directions or in R many polytopes, then you have some linear dependency on the R constraints that link together the polytopes. And this would mean that you could also move your solution, your supposedly vertex solution, a little bit and remain feasible, which would be a contradiction. But well, it doesn't help us so much that they are vertices, because well, the vertices of the QIs may be fractional, and that means you could have fractional variables in each of the polytopes. And if you have a linear number of fractional variables, it will be very hard to have a distance to an integer solution that is not linear. And there are concrete examples where you cannot. Now, our solution is, well, we simply replace each of the QIs by the convex hull of the integer solutions inside QI. And only then we relax the integrality constraint. What this helps us is now we know that already almost all of the variables are integer in a vertex solution. So this is not the end of the story. You still have to work a little bit to prove a good proximity, but we could show that if all the QIs are integral polytopes, or you replace them with the convex hull of integer solutions, well, then the proximity is independent of n. It is then a function of R, the mm, greatest entry of the AIs, and the so-called graver element norm, which I will not go into detail here. We now come to the final part of this presentation, which is about solving block-structured linear programming, and in particular the stronger relaxation. Here we make use of the Lagrangian dual. The Lagrangian dual is equivalent to the LP, but it allows us to lift some of the constraints to the objective function. Formally, it is a minimization problem of a convex function where we minimize over a vector lambda, which describes how much we punish deviation from the right-hand side in one of the constraints that we have lifted. We will lift there are many constraints that were added on top of the polytopes, because that way the problem again breaks into independent subproblems. So for a fixed lambda, we can compute this function, this convex function L lambda, by basically just optimizing over each individual polytope. Our strategy is to run each optimization problem on each QI with optimization direction that is derived from the optimal lambda star. The problem here is that we don't know the optimal lambda star, but quite surprisingly, this approach is still sensible. We first have to make a mild assumption on the algorithms that optimize over each of the QIs. Namely, we require that they access the optimization direction only by linear comparisons. So they may ask, is the first coefficient of the optimization direction greater than 4? Is it smaller than 4? Or similar? Or generally, they provide a vector A and a value D, and they ask, is A transpose Ci greater than D or smaller than D? Now, if we want to run the algorithm with the optimization direction from the Lagrangian dual with the optimal lambda star, then we only have to answer comparisons on Ci plus lambda star transpose Ai. And this is in fact easier than finding out the precise value of lambda star. Let us start with a simpler case where lambda is just in one dimension. So that means there's just one linking constraint. In that case, we can directly transform this linear comparison on Ci plus lambda star transpose Ai to just a linear comparison on lambda star of the form, is lambda star greater than D or smaller than D for some D provided by the algorithm. And well, here we use that L of lambda is a convex function, and lambda star is the minimal point of this convex function. Because now we only have to look at the gradient at the point D, and this will tell us if lambda star is smaller than D or greater than D. Essentially, we can just evaluate L of lambda at the points D, D minus epsilon, and D plus epsilon, and with these three values, we can find out on which side lambda star is. And for specific concrete values, we know how to evaluate L of lambda, because this is simply running all the n optimization independently. So in order to get a good running time, we have to be a little bit careful, because the naive approach would give the following. Suppose each QI can be optimized over in time t. So in particular, the number of comparisons is at most t. Then we might have to evaluate L lambda at n times t many points. And for that, we have to optimize again over all polytopes. So we would already get n times t squared running time, which we would like to avoid. But fortunately, we can um, uh, use that all the optimization problems are very parallel. So we can think of each of the QIs to be optimized over in parallel, and at each time step, we have to answer n many linear comparisons on lambda star. And these n many comparisons can be answered by just answering log n many concrete comparisons. And to do that, we will just order the right-hand sides d1 to dn by magnitude, and we will look at the median, in this example d3. For this median, we make the comparison is lambda star greater than d3 or smaller than d3. In this case, it is smaller than d3, and this will also solve the comparison for all um, values that are on the right of d3. And in any case, it will answer half of the comparisons. So if we repeat this log n times, we will have an answer for each comparison. And this would reduce the running time to t times log n times nt. So we avoid the additional factor of n here. A similar approach can be taken in dimensions higher than 1. And here, Megiddo's multidimensional search comes into place. This is essentially the same trick as we did with the median, but in higher dimensions and much more difficult. But it essentially says that instead of doing n comparisons, we can do 2 to the power of r times log n comparisons and answer all of them. This was used, for example, in his infamous linear time algorithm for linear programming in fixed dimension. But there's another problem, which is how do we answer one of these resulting comparisons? And well, we can't just evaluate L of lambda at 3 points and get the answer. But there's a nice technique by Norton, Plotkin, and Tardosh, who essentially describe how to answer such a comparison by doing 3 recursions into a lower dimensional subspace of R to the R. So that means we can answer a comparison on lambda star by solving a problem of the kind minimize lambda in S, L of lambda, where S is a subspace of strictly a smaller dimension than R. And well, in this problem, we again recurse to the smaller dimensional problem and so on until at some point we are in a 0-dimensional problem, which is again just evaluating L of lambda at one fixed point lambda. So I want to conclude by recapping our results. We have shown a new algorithm for block structured integer linear programming that breaks with the current augmentation framework, and it obtains the best running time for n-fold integer programming. We also give the first sophisticated algorithm for the linear programming variant of continuous variables, which also shows there's a we can use this block structure to get a faster running time. And in both cases, we are near linear, strongly polynomial, and we can parallelize the algorithm. Thank you very much for listening. And if you have any comments or questions, feel free to contact me by email.